Okay, for the first two lectures, I've been reviewing vector spaces on Rn because as we go into more abstract setting, it's hard to understand what's going on without having a good understanding of Rn. So let me just speak about some basic things that we saw in Rn. What can be done in Rn? Or maybe let me pose the question like this. What is linear algebra? Linear algebra is about things that resemble this. And if we have something that resembles this, then we can do stuff. What things can we do? Well, if you track the things that we were able to do, is one was that there was the idea of the basis, right? The idea of the basis is that you can choose a list of vectors so that all other vectors can be uniquely represented as a linear combination. That was what I was trying to show you. And once you choose the basis, not only can you represent a vector uniquely, you can also rewrite any matrix with respect to this new basis, right? And by rewriting the matrix with this basis, sometimes you are able to make the matrix look a lot simpler. For example, certain matrices had two linearly independent eigenvectors, and if you use those two as the basis for your R2, then we were able to take that 2 by 2 matrix and make it look like a diagonal matrix. And the reason we like diagonal matrices over regular matrices is that diagonal matrices are much easier to calculate, right? So along the way, we had the idea of eigenvalues, eigenvectors, and then we also had the idea of diagonalization. Now, these ideas don't seem to be that powerful, but indeed it's very powerful. And the reason being is that the Rn itself is such a simple kind of structure that that kind of structure can be seen everywhere. And therefore, anytime you see them, you can think about these things. What's the basis? If you have an operator on it, what are the eigenvalues, eigenvectors? How do you diagonalize it? There are so many places that this appears. One example that we were talking about was when you had subspaces, but that's still too abstract. What are some real-life examples? Like real-life examples, I briefly talked about it. It was like the audio, right? Audio signals. If you collect the space of all possible audio signals, they are going to form a vector space, right? Because, I mean, what's a vector space? You need two things. You can add, and you should be able to multiply any numbers, right? So if you have an audio signal, and you have another audio signal, can you add them? Yeah, you can add them. If you have an audio signal, can you amplify them? Yeah, you can multiply some number times 2 times 3 will make it louder, right? So this happens to satisfy the properties of vector space. And in fact, what digital audio does is it takes this audio signal and does a sampling. It looks at the amplitude at every point. So for CD quality, it's 44.1 kilohertz. So it divides seconds into 4,400, no, 44,100 little bits of times, and it samples the magnitude of the wave and stores that value as a number, right? So it's a very long vector. 1 second of audio will be a length 44,100 length vector. That's quite large. Yeah. But people hear CDs, right? And listen to music by doing such a thing, right? Now, because you can sample it and turn it into a vector, you might think, okay, so you can do that. So what? What's like so fancy about that? Well, the fancy thing that you can do is people figured out that instead of trying to write this as a bunch of like a signal at the first one plus signal at the second one and then signal at the third time frame. So these are individual time frames. You can definitely take an audio and write it as some of these individual audio signals, but there's another totally different way, which is to think of this as like a very low wave signal, and then something that's slightly higher frequency, and then something higher frequency, and you have some constant multiplied to it. So we're really taking linear combinations of these things. And some guy named Nyquist realized that, oh, if you need to represent 44,100, you just need 22,050 different wave lengths, and each of these are either sine or cosine. So you have like 2 different waves for each frequency, and then you add them and you can recreate this entire thing. So that's what the audios are, MP3 players are really doing. What it does is a lot of the music will have non-zero values at only certain waves, because like what is music? It's like you hit the key A in the piano, then there will be one place that corresponds to the frequency of A, and then there will be also the higher harmonics of this A that appears, right? So if you record something that's musical, then a lot of these things end up being close to zero. So indeed, when it's close to zero, then some people thought, what if we actually take these things that are close to zero and just set it as zero? Then we need less information. Would that still work? And people listened to the result and said, oh yeah, I can't really tell the difference. The ones that are close to zero, we can just set it as zero, and it's perfectly fine. And it uses some additional ideas to compress this so that the success story is that if the original music was 10 megabytes, the MP3 version was only 1 megabyte. And by doing that, all of the online streaming services were possible. Now, recently, maybe three years ago or something, there was a startup company named Tidal, backed by Dr. Dre and other people, which would not compress their music. They're saying, oh, the internet bandwidth has increased, so we can give our customers the true original form, not the compressed version. But it really didn't kick off because the customers, when they were listening to both versions, they knew there was slight improvement in quality, but not that much to justify a new service for just that. So MP3 success story still works out. Now, images are also vector spaces. So if you have a picture, how is picture stored? You divide this into many small pixels, right? So you know what a pixel is? Minecraft, you can think of Minecraft, right? Uh, so in Minecraft it's 3D, so they don't say pixels, they call it voxels, because the volume pixel. But it's the same kind of thing. It's like small dots, and you can color them in different colors. Everything has RGB values, and then you color differently. And if these pixels are small enough, then you have a photo that's if you look at it, you can't really see the pixels. You see the picture. Now that's also a bunch of numbers at each point, right? So anytime you have an array of numbers, basically all digital data, multimedia data, if you have them, you can think of them like vectors. And once you have vectors, then the next question is like, what kind of basis can we choose? And the basis you can choose for this one is again like sinusoidal waves, and that's two-dimensional. So you can have like sinusoidal going that way, but also this way. You multiply those two functions, you get a two-dimensional wave with different frequency in the x direction and y direction. You add them up, and then you can again represent pictures like that. And such a way of representing a picture is called JPEG, right? JPEG, JPG. Most of you, when you upload a photo to your Instagram, what format do you use? JPG, right? Because it takes up less memory than a BMP file. In fact, I'm pretty sure if you upload a BMP file, the Facebook people will convert the regular BMP to JPEG before they put it on their servers, because again, JPEG is like 1/10 size or even less than a BMP file that's uncompressed. So that's another idea. Now, how many of you here took the applied real analysis class, which is, I know you have, this is like also known as PDEs. How many of you took that class, PDE class? Okay, only two, all right. So another place that this kind of idea happens is that if you have a, well, you've already seen this in Calculus 4. If you try to solve a differential equation that's homogeneous, then the solution sets form a vector space. And so what was it? So for example, if you have y double prime minus 4y prime plus 3y equals 0, what's the general solution? Then the solution looks like e to the x and e to the 3x, c1 plus c2. So everything looks like this with different values, and so all the solutions look like that, which means that it's a two-dimensional vector. You can choose two different numbers of parameters. So that's that. And in linear PDEs, they take this furthermore, and they think about there's something called the separation of variables method, where you loosen some conditions, put some zero in the boundary conditions, and that gives you a set of functions that can form a basis for the generic solution of the differential equation. So if you're solving PDEs, heat equation, wave equation, and all these things, whenever you do a separation of variables method, what you're doing is you're trying to find a basis actually using all these ideas, eigenvalues, eigenvectors associated to the PDEs, because PDEs are like a differential operator applied to functions. So all of this is relevant. Even diagonalization is relevant in PDEs as well. If you can grasp how linear algebra is used in that class, like you end up understanding both much better. Another place that this linear algebra appears is when you do something called the differential geometry. Now that's like a graduate topic. We do have a differential geometry course here, which is just limited to surfaces and curves in 3D. But if you go to grad school and take these harder math courses in differential geometry. In differential geometry, they talk about curved soft surfaces that's like in higher dimensions. So we can only visualize in 3D, right? But you can think of like four-dimensional space, which is like space-time. That's Einstein's general relativity, and even higher dimensions. And when you have all these curved spaces, which is needed for general relativity because gravity will like take the space and warp them somehow. So to describe how gravity acts on things, you need to know how the space is curved. And for a better description of this, you have to talk about in a curved, so if you have like a curved terrain, then at each point you have to talk about a tangent space, because the curved space itself is hard to think about, but well, another way to say it is like at every point in this curved space, if you think about all the possible directions you can move instantaneously, they form a straight space. So it's just like in a curve, what is calculus? Calculus is like thinking of all the tangent lines of a curved thing, right? Because at every point, if you look at locally, it looks like straight line, right? So in a curved space, if you think about all the possible directions that you can move, they form a vector space as well. And these tangent vectors, so-called tangent vectors, become very important in deriving formulas and being able to come up with calculations in these curved spaces. So that's, again, very important. And again, if you have tangent spaces that are always changing, and it's just not a single vector space, it's like parametrized vectors with the parameter being each point in the manifold. And at every point, you have to think about how to come up with the basis, because you need to choose a basis in order to describe the vectors at every point, right? Then there are like various strategies in finding the correct choice of basis to write the formula in a more efficient way, and so on and so on, okay? So all of these are what comes out of linear algebra. Oh, I didn't even talk about the other guy, which is like in data science, there's something called PCA, Principal Component Analysis, and that was the homework in the first, that's a makeup for our missed class or Friday, right? So if you looked at the singular value decomposition video, that gets used in something called PCA, and that's a really nice way to take a large data and figure out the most important bits of the data from the large one. So there's so many places where you end up using this linear algebra. So you can kind of think of this linear algebra as a foundational course. And the power of linear algebra comes from the fact that although you're used to thinking of Rn, you forget that Rn is the vector space. Rather, you think of some abstract space, and you kind of think about the properties of that space and describe everything abstractly. And the more abstract you get, the nice thing is, like, once you find something else that satisfies all the properties that's required, then you can play everything on that new venue. So that's the power of linear algebra. Anytime you can take something that's familiar and make it abstract, then other things that you thought didn't have any relation to this familiar object, well, you find that they both satisfy the same kind of properties. So you can treat this one like the one that you already know. So that's the power. Being able to think about. So let me put it that way. Why is math so powerful? Like, I know some of you might want to become a teacher. I want to pose this question. Why is math so powerful? The power of math is in its abstraction. See, long time ago, probably the cavemen were looking at things and thought, okay, you have one rock, another rock, two rock, okay? And then he was watching the sky, and then he thought, okay, one bird, another bird, two birds. And these individual things don't necessarily have to be connected in any way, but at some point, oh, there is this concept of two. The moment you can abstract the concept of two, then you can talk about arithmetic. You can add stuff. See, animals can only intuitively know values up till like 3 or 4, right? But humans can do like 125 plus 7. That's not a problem for us because we can abstractly understand what numbers are. See, of course, two birds and two rocks are completely different things. And if somebody didn't have any concept of numbers and you try to explain that, they might think you're crazy. But once you know the power of abstraction, then by abstracting this concept of two, you can apply in so many different places. That's why it's so powerful. Okay? It's the same idea. If you can take what's known as vector space, the Rn, just take all the properties there and then come up with a new definition, then with that definition, that abstract definition, you can apply it in so many different places. That's why we're doing this class. Does that make sense? Okay, so this is really the first class. Okay, we are doing this linear algebra done right. Algebra done right by Sheldon Exler. I think our library has a digital version, so you can legally download it. And if somehow you don't, if it's not there, then he has his website which has the older version, and it's not that different if you don't want to pay for it. But it's a really great book. Many colleges adapt this book, so we are going to do the same thing. And I'll try to use the examples used here, but I wouldn't necessarily like touch on everything that's said in the book. But a good way to get the most out of this class is to first listen to my lecture and go back to this textbook and try reading that corresponding portion and see how much you can understand it. Because just trying to understand it without any clues or any tips, it's hard. But once you follow my lecture, then it'll be much easier following the book, okay? All right, so it's really chapter 1 that we're trying to start. Chapter 1. And because I don't know the chapter numbers and all that, for my other classes, I never write notes, but I had to write notes here because occasionally I'll put some numerics on here. That means that's the number that corresponds to the textbook. So see, as you review the video, try to see the corresponding parts in this textbook. Okay. All right, so chapter 1 introduces vector spaces, but before it introduces vector spaces, it talks about fields. Okay. So what's a field? Well, instead of me giving you the definition of a field, I'll just say set of real numbers R that we're so used to, and also set of complex numbers, or Q, which is a set of rational numbers. Rational numbers are numbers that can be represented as an integer over integer, okay? These are examples of fields. Okay? So we're going to go backwards. Rather than me giving you the definition of a field, I'm going to start from these examples and say what kind of properties these sets have. So they all have two operations, two binary operations. By binary operations, I mean you have two objects and then you can do something with these two and get a single number. Okay, so one of them is addition. What's the other one?
Multiplication.
Multiplication, right? Okay, so addition and multiplication. Of course, there's the subtraction and division, but I'm going to take them as like inverse operation of something. So we're only going to think of these two operations. So all of these have addition and multiplication. So usually when the proper way to write down a field is like R is a field, but this is just a set. When we say this is a field, we're really saying that R equipped with the addition and multiplication is a field. So you write this as a 3-tuple. All right. So what kind of property does addition and multiplication have? I mean, you learned something of that sort in high school, although you probably didn't see the point why you would do such a thing. So can you name any properties of these addition and multiplication? Or if you can't, how about this? You try to explain to me a property if I say the name. Distributive property, what's that? Distributive property, what's that? Do you know what this is?
I don't know how to put it in words, but it's like
Yeah, give me the formula.
A parentheses B plus C parentheses is equal to AB plus AC.
AC. Yeah. Right? That's distributive property. Right? This is a property that involves both addition and multiplication. Right? Okay, so that you probably heard of it. Have you heard different words that's similar to this? Like in this area, have you heard different words? What other words are there?
Like commutative.
Commutative, very good. So commutative, which is A plus B equals to B plus A, and A times B equals to B times A. Okay. What else? Huh? Associative, very good. And sadly, I haven't noticed anybody doing this before COVID, but after COVID, my students' algebra skills went so bad that so many people say, okay, 2 times 3 times 4 is 6 times 8. Have you seen this? I've seen people doing that, yeah. That's wrong, right? When you have a multiplication, what do? You have to multiply to only one of them, right? That's associativity. So if you see A times B times C, that means, this really means AB times C, because you have to do the operations in the order that's written, right? But what this formula is saying is that it really doesn't matter whether you multiply A times B first or B times C first. Okay, that's what the associativity is saying. Now tell me what the corresponding one for the addition would be. Okay, parenthesis of A plus B plus C is?
A plus parentheses B plus C.
Good. That's associativity, right? Okay. Do you know anything else?
Identity.
Yes, identity. So you have identity, and you have 2 types of identities. You have the identity for the addition, and there's the identity for the multiplication. So you have A plus, what's the additive identity?
0.
0. So A plus 0 is 0 plus A, which is A. And then multiplicative identity is 1, so A times 1 is 1 times A equals to A. That's identity. And then this one's a bit harder to remember, but there's something called an inverse, so that for any element A, there's an inverse element so that you get a 0, okay? For any element A, you have a multiplicative inverse element, which is the reciprocal, and that's equal to 1, but here you can't have A as 0, okay? So these are all the properties of a field. And RCQ satisfies all of them, okay? Now, let's see. One way to understand a abstract definition of something is to find examples where it is not. Some of these fail, okay? So let's think about the following. What about Z, set of all integers? Okay. For a set of all integers, is this true? Integers like 1, 2, 3, and negative numbers, right? Including 0. That's true. How about this? That's also true. This is true too. Okay. Then what about this one? Definitely integers have 1 times 1 is okay. You can add 0, that's fine. How about this? Even this is okay. But what about this? This one fails, because if A is 2, 1/2 is not an integer. So set of integers, you put it as Z, okay? So this Z set of integers is not a field. Okay, so our definition of a field is it's a set equipped with addition and multiplication where the addition and multiplication and the set satisfies 1, 2, 3, 4, 5 properties. Okay, actually, if you count the multiplication and addition separately, you actually have 9 properties. Okay, so it has to satisfy 9 properties in order to be a field. Z satisfies almost all of them, but not this last one. And in such a case, if only the last one fails, there's something called a ring. You're going to learn this if you're taking the abstract algebra course, okay? It's called a ring. All right. But there's something that satisfies over here most of it, except this this thing. What is that? What satisfies these, but not this one?
Matrices.
Matrices. Matrices have multiplication, but matrix multiplication is not commutative. There are examples where if you have 2 matrices, A times B is not the same as B times A. So matrices are not commutative. You can take a subset of matrices that are invertible. So there's something called GLR, say GLR2. These are 2 by 2 matrices that are invertible. If you do that, then it's going to satisfy all of these except this one. It's going to satisfy this one. There's a multiplicative identity, which is the identity matrix. It has this one, and you can also have this one because it's invertible, right? This one, oh, no, just a minute. Oh, you have to, sorry, this one doesn't have 0 in there, so you have to put a 0 attached to it. That's 0. So this, am I right? Yeah, I'm right, okay. So this set would be what's known as a division algebra. So there, like, if you take the abstract algebra course, you have so many different names for things that are almost like a field, but it fails certain parts, okay? So that's what it is. Yeah, just one more. If you have, so this, if you, oh, how many of you took the applied algebra? No, you took applied algebra. Okay. So in applied algebra, you learn something called a group, which is like a group is a set with just a single operation, where there's the multiplicative identity E. Oh, and G H I is G H I. It also has an associativity, and then I'm not going to write it because this one's not so important. And then there's the inverse. Every element has an inverse so that it recovers the identity. If something like that is true, then it's called a group. This is called a group. And if you also have commutativity, then it's called the commutative group or abelian group. Plus commutative gives you a abelian group. And in that viewpoint, there's another language to describe what a field is. A field is a set with two binary operations, addition and multiplication. The set with addition is an abelian group because it has commutativity and it also has additive identity and additive inverse. So R plus is an abelian group. Now R times is not an abelian group because zero element doesn't have a multiplicative inverse, but if you take R and take away the zero, that's called that's again, so R take away the zero element and think about this binary operation. This is an abelian group. So it has to have those two. And then in addition to those two properties, that's an abelian group under addition and abelian group, almost an abelian group under multiplication, with the additional property to connect the two operations, which is the distributive property. That's what it is. Okay. So what can we do with this, you might ask? Like, okay, so we have R, C, Q, and these things, and you have these properties. Like, what does that help us? Well, it does help us because you can find other fields. So there's something called modulo. Well, if you took the applied algebra, you know you learned the modulo space, modulo set. So it's like think of 0, 1, 2, 3, and then 4. And this is mod 5. Okay. So what we are doing is like you're thinking of all the integers, but every integer you can divide by 5, and if you divide an integer by 5, the remainder is either 0 or 1 or 2 or 3 or 4, right? So that's called the modulo system. And surprisingly, modulo system satisfies all of these, and it even has an inverse. So think about this. If you have 3 and 4 multiplied, 3 times 4 is what? 12. Yeah. But this is what's known as the equivalence class. So 12 with a bar is same thing as another number that has the same remainder under 5. So if you take 12 and divide by 5, what's the remainder? 2, right? If you had like 12 candies and 5 people had to divide them, everybody will get 2, but then 2 will be left, right? So 2 is the remainder. So this is the same as 2. So you can see that 3 times 4 is 2. Okay? And you can even see that 3 times 2 is what? 6, but 6 under mod 5, that's 1. Oh, that's an identity, right? Multiplicative identity, right? So 2 bar is actually, it functions like 1 over 3 in this numeric system. It's strange. Okay? So you can find other, so these are called ZP, so modulo P, and P has to be a prime. If it's not a prime, then it's not a field. So that's a field. And you might still ask, like, so what? What is this so important? Well, it gets used in encryption. So the reason that you can confidently go to Amazon, type in your password, and give your credit card, and hackers will have real trouble finding out what you bought or what your credit card number is because there is something called RSA encryption that's built on this system. And it talks, because you can have all these multiplication and addition. You can add 2 things too, right? This would be 7, which is equal to 2. So addition and multiplication is provided, and if you have them, then you can also take powers. So you can take 3 to the power of 5. All of these are afforded because you have all the operations, binary operations that you need. And then you can use RSA. This is rather complicated. It's going to be like another 1 hour to explain what RSA is, but it's basically what allows us to buy stuff on online. Okay, so it's all really powerful. Sadly, most of the useful math are out of reach. You have to go to grad school to see them in action. Yeah, that's the sad part. So a lot of the undergrad math will graduate with a math degree and think like, what did I just learn? Like, it doesn't seem to be used anywhere. But once you start going to grad school, and not just math grad school, but like engineering grad school or other places, computer science or stuff like that, data science, then you start seeing math in action, then you'll see why we do such a thing, right? Okay, so we defined what a field was. Field is this these 9 properties. Now let's talk about vector spaces. And rather than me telling you what the definition of vector spaces is, let's just like come up with some observations that we can come up with the usual vector space, and then try to organize them as the axiom of a vector space. So, so think of one nice example, simple example. We were working with R2 and R3 a lot, right? So on R2, when we think of R2 as a vector space, okay, first, what kind of operations were we able to do on R2?
Addition and multiplication.
Yeah, so we had 2 vectors, so we had 2 vectors in R2, and we were able to add, and we couldn't multiply UV, but there was a constant a scalar in R where we could multiply to U. So this is vector addition, and this is scalar multiplication. Okay, and what we need to do is we have to individually list their properties, like what are the properties of the addition, what are the properties of the scalar multiplication, and once we list them all, we also have to think about the combined properties, like what's the property that uses both of them, okay? The easiest part is the vector addition. So what properties does vector addition satisfy? Can you name them?
Associative.
Okay, associative. So number one, the addition satisfies associative, which is that u plus v plus w is same as u plus v plus w. Okay, what's another one? Commutative, I want to use that later, but that's definitely true. What else? Identity, which is u plus 0 equals to 0 plus u equals to u. What else? I got commutative, there's just one more. Inverse, yes. So inverse, which is u, there's another element here that gives you 0. And then commutativity, which is u plus v equals to v plus u. Okay, and as I said, the first three properties mean that this vector space, we'll call this vector space as capital V, okay? Yeah. So V is a group under addition, and especially because it satisfies the commutativity, we say V plus is an abelian group. Okay, that's what we observe. Okay, now what about the scalar multiplication? What kind of property should the scalar multiplication satisfy? Oh yeah, distributive definitely, but that kind of connects the two. Distributive property in a field is also like that, right? It connects the addition and multiplication, right?
Inverse?
Huh?
Inverse?
So definitely it has an inverse, but that's because R is a field. So that's like a property of this. We want to see the property of how the constant multiplied to a vector satisfies, what it does. Okay, so scalar multiplication is an operation between the field element and the vector element, okay, when those two are multiplied. Well, it has two properties. One is the number one. See, fields always have a multiplicative identity, which is 1, right? When you multiply that 1 to any vector, that gives you itself. In other words, 1 multiplying by 1 doesn't do anything. That's what this means, okay? And there's another property that looks very similar to a associativity, but it's slightly different. So let's say A and B are both in R. So A, B are in R. And this is same as A times BU. Okay. Now, if you end up in math grad school for some reason, because somebody convinced you to do that thing, I don't know, then there you're going to learn this in a more general setting, which is called the group action. So that's a more technical word. In other words, when you operate by an identity element, you don't want it to change at all. Okay, and if you multiply, this is like function composition. Function composition should, if you compose the function and then apply to a vector, that should be same as applying scalar multiplication once and then doing it later. So that's this is like associativity, but it's not. It's not associativity because associativity requires all of the three to belong to the same set. But here, A and B belong to R, whereas U belongs to vector space. So it looks like associativity, but it's not. Okay. So this one is called a compatibility condition. So yeah, in the group action, this is called compatibility condition. All right, and then you said distributive. Thank you. That's very good. So that's but there are two kinds. So tell me the distributive property. How would you write it? A times what? Two vectors, u and v, right? That should be AU plus AV, right? But there's the other way around because there's addition in the scalar as well. So there's an addition between vectors, but scalars can be added. Right? So A plus B, what would this look like? A plus B times U is going to be AU plus BU. Okay? So how many are these? These are 8 conditions. So I wanted to erase everything and rewrite, but this is already very well organized. So let me say a vector space V over a field F is a set with vector addition and scalar multiplication satisfying these 8 conditions.